we have draw the best Lewis structure for CH2O. Based on Lewis structure for that, consider the following: the electron geometry, the strongest intermolecular force the molecule would exhibit, and it lists out 3 of them, and then the last one is the molecular geometry. And yes, electron geometry and molecular geometry can be different at times. So the best Lewis structure for CH2O. So carbon is the 14th column element, so that is 4 electrons it can donate. Hydrogen, 1 each, so that would be 2 electrons there. And oxygen on the 16th column would be able to give 6 electrons. So that's 4 plus 2 plus 6. So CH2O. In total, we're working with 12 electrons. Okay. Now, because carbon has the most unpaired electrons, we'll put that in the middle. And we have C, H2, and O. So here, the hydrogens are already done. Okay. They are sharing one of their 1 electrons. So we don't touch that. Oxygen, on the other hand, is sharing it's sharing 1 of its 6. So we need to add 5 more. Okay? 5. There. Carbon, on the other hand, is sharing 3 of its 4. So we just have 1, 2, 3, 4. So that being said, these 2 here should come together to form a double bond. So what we really have is as the most stable structure, this is what we would get for CH2O. As you can see here, everything is filled as octet rule, and also should be formal charge of 0, because carbon's net formal charge of 0 is 4 bonds, which is what it has. Oxygen, on the other hand, is 2 bonds and 2 lone pairs, which is also what it has. So we're good there. And the hydrogen is just 1 bond, so we don't have to worry about that because that's exactly what it has. So now for the electron geometry, okay, we need to count how many, pairs it has, whether it's bonding pairs or lone pairs. So for this, it has 1, 2, and here's the tricky part. Even though it's a double bond, it still counts as 1 bonding pair, okay? Because of that, alright, the reason why we did this is now it has 3 bonding pairs. And so the shape, based on this having just 3, its hybridization is sp2, okay? And the shape is trigonal planar. Alright? So that will be the electronic geometry. What will be the strongest intermolecular force in this molecule? Let's look at these, okay? Everything has London dispersion force, so that's technically not incorrect, but I'm sure we can get stronger than that. We have dipole-dipole and hydrogen bonding. Hydrogen bonding, the reason why I skipped dipole-dipole is because hydrogen bonding is a little bit easier to solve. It only occurs when these 3 happen. Fluorine attached to a hydrogen, carbon, oops, sorry, not fluorine. Carbon, nope. It is, yes, oxygen, hydrogen, fluorine, hydrogen, and the last one, nitrogen, hydrogen. These type of bonds here are what they refer to as hydrogen bonds. Unfortunately, none of those are present in this molecule. So even though hydrogen bonding is stronger than London dispersion, there's none here we can see. Now dipole-dipole, that one is a little bit more intricate. That one is based on the electronegativity difference. So between carbon and hydrogen, this actually, so carbon is 2.55, hydrogen is 2.20, so the difference is 0.35. Those type of bonds are typically considered non-polar covalent bonds, so they're non-polar. But the carbon and oxygen has 3.44. So because there is a, let me just do the math, 3.44 minus 2.55, there's a 0.89 difference. We're now in the range of a polar covalent bond. So this oxygen would exhibit a greater electron affinity than this carbon here. Okay? So because of that, the molecule is polar, and so because it's polar, it actually would exhibit a dipole-dipole bond when these I guess CH2Os pass each other. The more negative oxygen side will be attracted to the more positive carbon side. Okay, so with that being said, dipole-dipole is stronger than London dispersion, so the strongest force here would be dipole-dipole. And now the last question, the molecular geometry. This one is a little bit tricky because it's going to be very similar, in fact actually the same as electron geometry, because we have 3 bonding pairs, but we have 0 lone pairs. Meaning that because it stays the same of 3 bonding pairs, the name carries over to where it is a trigonal planar molecular geometry. So these are the 3 answers we should get. The electron geometry is trigonal planar, the strongest force is dipole-dipole, and the molecular geometry is also trigonal planar. Let's see how we did. So as I drew it, it should be a double bond. Perfect. This is what they should get. A double bond with the oxygen and 2 CHs. There we go. So now, the answer, trigonal planar, that's the electron geometry. Dipole-dipole, correct again. And because it has 3 bonding groups, it's going to be trigonal planar again. So this is correct. And now let's move on to question number 17.